Okay, in moments in center of mass, there are 4 learning objectives: to find the center of mass of objects distributed on a line, locate the center of mass of a thin plate, use symmetry to help locate the centroid of a thin plate, and apply the theorem of Pappus for volume. Okay, so the center of mass is basically the location that we would use to balance an object. Okay, so I want to start off very simply talking about masses along a line. And if you think of this kind of very similar to a seesaw, then you can really understand the concept. Okay, so there is what we call a fulcrum. I'm going to make my little fulcrum right here. It is a little triangular thing. And I'm putting my fulcrum right now at 0. Okay, and so I want to just add this one little line in here right before this. I want to put in masses along a line. Okay, so here I'm going to put a mass M1, and it's at location X1, and I'm going to put another mass X2, M2, at location X2, and I'm going to put another mass M3 at location X3. Now, clearly, if 2 people who weigh the same get on a seesaw and they are equally distant away from the seesaw, then the seesaw will balance. But if one moves closer, then it changes how the seesaw is actually going to balance. So over here on this side, this particular, on the left-hand side, we have what we call negative torque. And that is a desire for this to rotate in that direction. And on this side, we have positive torque. And that is a desire for it to rotate in that direction. So each mass, all right, we know. And then of course, force is equal to mass times acceleration. We know that. So there's a force, F1, that comes from this mass, M1 times G, that wants it to rotate. A force F2 equal to M2 times G that wants it to rotate. And a force F3, which is equal to M3 times G. So we already know what each of these forces are, where G is the constant of gravity. Okay, so each force, all right, wants to turn the axis about the origin. Okay, so the torque is its turning effect. So the torque is what we're going to call its turning effect. That's effect, not affect. And it is equal to the force, which is MI times G. So that's the force, but it's times the distance this thing is from the axis that it's going to go. And it's a signed difference. It can be positive or negative depending upon where this thing is located. Okay, so now I can talk about the system torque for the whole thing. So now let's think I have 3 kids on 3 different children that are sitting on this seesaw, and they have different weights. So the question is, where can I put them so that this thing is going to balance? So we have a system torque, and the system torque says add them all up. All right, so if I sum them all up, that is the sum I equals 1, and in this case, it is 3, but n, depending upon if you have n kids sitting on this thing, is mi times g times xi. And for our problem, okay, n is 3. So this is simply m1 g times x1 plus m2 g times x2 plus m3 g times x3. So far I have not done anything difficult. Okay, so I can pull g out because g multiplies by everything. So I get g times m1 x1 plus m2 times x2 plus m3 times x3 as I factor g out. Okay, and this thing becomes the moment about the origin. Okay, so this piece right here, don't include g, but this piece is the moment about the origin. Okay, so I can now give it a general name. When n is not equal to 3, I'm going to call MO. This is the moment about the origin. It just says sum up I equal 1 to however many you have of the xi's times the mi. Okay, so that's the moment about the origin. Okay, so now that I have defined what that moment is, now I want to say, let's suppose I put the kids there, but I want to move the fulcrum. Okay, so before I was trying to move the kids. Now I want to move the fulcrum. Okay, so we want to place the fulcrum at a location that's going to balance the system. Okay, so now what's our goal? So now our goal is to place the fulcrum okay, to balance at a location to balance the system. All right, so so now I'm going to go back to the original picture, right? But I'm going to change it ever so slightly. So I'm going to draw this again. I'm going to leave 0 where it was. So 0 is here. And then I have this one mass M1 still at location X1. And I have this mass M2 still at location X2. And then I have this mass M3 still at location X3. And now what I want to do is I say I want to put the fulcrum right here. Based on the masses, I need my fulcrum right there. So this point is going to be for me the center of mass, which I'm going to call X bar. All right, so now the torque all right, of each MK, all right, about X bar is going to be, we're going to take the distance, it is XK, subtract X bar, and multiply by the mass, MK, and then the gravity. Okay, so note, this is a signed difference. If it's on the left, it'll be negative. If it's on the right, it'll be positive. So this is a signed difference. Okay, and of course, MKG is a downward force. So this is a downward force. All right. So now I want my system in balance. So that means I can't have a torque on trying a positive torque or a negative torque. My system in balance means the sum of the torques is 0. So for a balanced system, in other words, where these children are sitting on this seesaw, I need the sum of their torques to be 0. Okay, so that's the basis of what I'm trying to do. So now I'm going to solve for what X bar must be. Based on how much each kid is, how much each child weighs, and how far they are from this X bar, I can determine to you what X bar has to be. So let's do it. So I need the sum of all the torques to be 0. Well, this one is the torque about MK. All right, so the sum of all the torques, okay, I think I'm using K. Well, that's going to take XK, I'm going to subtract X bar, I'm going to multiply by MK, and then I'm going to multiply by G and set that thing equal to 0. Remember, this equation above is the torque for just the one MK. Now I'm adding them all up. So I'm adding the torque for every student or every child that's sitting on this seesaw. Okay, well, just like before, G is a constant, it's a number. All right, depends on whether my mass is in kilograms or whether it's in pounds, G changes. So I can factor G out and get the sum. I'm going to drop the K equals 1 to N because we know that's what it is. I'll put it back in later. So now I get XK minus X bar times MK G. Oh, I factored out G. That was the point. Is equal to 0. So let's distribute. So now we're going to get G, the sum. Inside, I'm going to get XK times MK. Oh, minus X bar times MK is equal to 0. So now I end up with 2 sums. And I can actually divide both sides by G, so G is gone. Don't need it. Once I divide by G, it's gone. So now I get the sum of XK MK minus the sum of X bar MK is equal to 0. So I'm going to get the sum of X bar MK is actually equal to the sum of XK MK. Now, XK MK should make you think, oh, I've seen that before. XK MK, well, that was for each one. Where is XK MK? Right here. That's its particular moment about the origin. So we summed them all up. Okay, X bar is a number, it's a constant. Let's pull it out. So I get X bar times the sum of MK is equal to the sum of XK MK. And now I have my formula. So I get that the center of mass X bar, so X bar is the center of mass for the system. It is the sum K equal 1 to N of XK MK divided by the sum K equals 1 to N of MK. Now, the top is just the system moment. So this part is the system moment. And then the bottom, that's just the total mass of the system. Because we're adding up all the masses. So that's the system mass. Okay, so that is, so basically, if I just have a bunch of points, I can tell you what the masses are and where they sit, then you can tell me exactly where this X bar, the center of mass or the fulcrum, should go. Okay, so let's say I have here's my bar. Here's 0. I have a mass M1 and it's located at, let's say, -3. I have a mass M2 that's located at 2, and I have a mass M3 that's located at 5. Let's put it at 5. Okay, and I tell you M1 is 80 kilograms. M2 is 71 kilograms. Nope, that's too much. Let's make this kid 50 kilograms. And we'll make this kid 35 kilograms. Okay, and so now I have a really big adult, actually, that's an adult, 80 kilograms. Okay, 50 kilograms and 35 kilograms. The question is, where's the center of mass? What is the center of mass? Okay, well, you have to add up the total masses. We need that for the bottom. So the sum of the total masses is 80 plus 50 plus 35. So that's 165 kilograms. No, it's not. Yes, it is. Okay. And then I need to find the system moment. Okay, so I'm going to get 80. The sum, the system moment is xk mk. So that's going to be -3. Actually, we're going to do this the fun way. I like this. We're going to do this the fun way. This is -3 times 80 plus 2 times 50 plus 5 times 35. -15. Okay. All right, so our X bar then turns out to be -15 over 165. And so this thing is almost at 0, just a little bit off from 0. So yes.
Sorry to interrupt, but is it supposed to be 5 times 35 kilograms? You put 25.
Oh, thank you. Thank you. Uh-oh, now it might not take the whole thing. Plus 5 times 35. Yeah, it's not going to take the whole thing. I got to do it again. So I had -3 times 80 plus 2 times 50 plus 5 times 35. Well, maybe it is 35. Okay, that's my answer. It is 35. Okay, so then this becomes 35. Okay, so it's going to be just a hair past 0. Okay, that's where it would go. Okay, so that's how we do that. Let's look at wires and thin rods. So the next thing we want to do is find the mass and centroid. So we want to look at the mass and the mass of thin wires. I'm going to scroll back to this just for a moment and underline this in red because I like my notes to be neat. And then I'm going to scroll down here and underline this in red because this is the next topic, mass of thin wires. Okay. All right, so we want to find the center of mass of a rod or a wire, and we're assuming this thing is really, really thin. Okay, so our goal is to find the center of mass of a rod or a thin wire. Okay, so this is where we're going to actually start to get into some calculus. Okay, because up until here now, we haven't done any calculus. So I'm going to draw a thin, I'm going to derive this thing. So this is the derivation, guys. The derivation helps to motivate the understanding of it. So we're going to assume that this thing is really, really skinny. Okay, so it's super, 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 super thin. Okay, and it goes from A all the way up to B. And I'm going to take a little tiny section of it. So I'm going to take this section of it right here, from here to here. And this little piece I'm calling delta xk. Okay, because I'm going to divide this thing up into a bunch of little intervals, and that's the kth little change of piece. Okay, and then its center is going to be xk. All right, so what I want to do is, let's say we attach a mass and that mass is going to be delta mk, and it's going to occur at xk. So there's, in this whole region, this thing here, there's a mass. Okay, and we're assuming, we're going to, for a moment, think of it as centered at xk. Okay, so what have we used before? Well, we know that from before, the center of mass is the system moment divided by the total mass of the system, or the system mass. Okay, so for us, the system moment is still the same. All right, so the system moment well, we're going to approximate it just like we did before by the sum, k equal 1 to n, of the xk's but this time I'm multiplying by a mass delta MK, because that's the mass that is attached to that one little space. Okay, so you can still think of it now. We don't have children sitting on something, but we're thinking of a mass of whatever this wire is, and it may not have the same density all the way through. So the mass will be different. Okay, so now mass, so density is mass per unit volume. Okay, but we're in one dimension. So density is mass per unit length. Okay, I don't have a 3D thing, I have a 1D thing. So I can't talk about the area, I can't talk about the volume, I can only talk about the length. Okay, so therefore the density at any piece, so the density at xk is going to be the change in mass over the change in length. So now, and this is approximate. So now I have a formula for what my mass is. So my mass, little delta MK, is approximately delta of xk, whatever the density is at that point, times xk. So that's what my little change is. Okay, so let's put it back into our formula. I told you before, these three little dots mean therefore. All right, so therefore x bar becomes the system moment, and the system moment is the sum k equals 1 to n of xk times delta mk. All right, and then that is over the system mass, which is the sum k equal 1 to n of just all the masses, which is delta mk. But I know what delta mk is now. So this becomes the sum k equal 1 to n delta xk. I apologize. I don't want delta xk, I want xk. I need xk times delta of xk times now I see my mistake. That's why I'm confused. This is supposed to be the change in xk. So this is the change in xk. Okay, and that whole thing is divided by the sum k equals 1 to n of delta of xk times the change, or that little piece, mk. All righty, here's where the calculus comes in. Okay, so calculus comes in is that we're going to take this partition and we're going to let the length of the delta k's go to 0 as n goes to infinity. And if you remember, when that happens, the sums become integrals. And so now we get that x bar, this is our center of mass, becomes the integral from a to b of x times delta of x dx, divided by the integral from a to b of delta of x dx. So now we have a formula to be able to find the center of mass. Now, before I go on, I hope that you followed my derivation. If not, please go back over it. But we want to make the notation. We're going to use dm, where we had before delta m, we had delta mk equal the density at xk times delta at xk. Well, we're going to take that thing and we're now going to come up with a differential for the mass. So dm is always going to be delta of x times dx. So another way of writing this is x bar. It's the integral from a to b of x dm divided by the integral from a to b of dm. Okay. All right, so we're going to have some definitions. All right, so m naught is still the moment about the origin. And so m naught, simply the integral from a to b of x, delta of x, is still the numerator, dx. That doesn't change. M is the mass. So m is the integral from a to b of just delta of x dx. And then x bar, which is the center of mass, well, x bar is m naught over m. Okay. So here's my example. So say we have a thin rod that is 10 meters long. So we're given a thin rod that is 10 meters long, which thickens from left to right by the density function equal to 1 plus x over 10. So clearly the density at 0 is just 1, but the density at 10 is 2, and it just gradually gets more dense. Okay? We want to find the center of mass, x bar. Okay, so I know delta. First thing I need to do is find m naught. M naught's going to be integral from 0 to 10. I'm going to need x. I'm going to multiply by the density, 1 plus x over 10 dx. It is just that simple. This is the integral from 0 to 10 of x plus x squared over 10 dx. And this turns out to be 250 over 3, and this is kilogram meters. So that's the system moment. Okay, the mass of the wire, the integral from 0 to 10 of just the density, 1 plus x over 10 dx. And that little integral turns out to be 15 kilograms. Okay, so then x bar is going to take m naught and divide by m. So that's going to give me 250 thirds. And then I'm going to divide that by 15. Notice this is kilogram meters, and this is just kilograms. So when I'm done, my answer is in meters, which is the location. And this turns out to be 50 over 9 meters. Okay. Now, if I actually did 50 over 9, uh-oh, that's wrong. 50 divided by 9. That's 5.56. So that's actually not in the middle, but it's a little bit further down where it's starting to get a little thicker. Okay, so that's the center of mass for that problem. Any questions so far? Because I
Can we leave our
haven't.
answers as a fraction?
Oh,
no?
50 over 9 is perfect. I just wanted to let you know that it was a little bit more than halfway past the center of the rod. It's not directly in the center.
Okay, thank you.
Okay, so now this is where we get stuff. Now we're going to 2D. So we started with this mass in a system like on a seesaw kind of thing. Then we went to finding the mass of a thin wire. So let's look at the mass of a plane region. Okay, so for the mass of a plane region, I now am going to still compute the system mass. I still need to compute now the center of mass, but the center of mass of a plane region now has an X location and a Y location. So when I go to compute the center of mass, and my center of mass is right here. And this is Y, and this is X. I'm going to have to give you a density, which is now going to be mass per unit area. Okay, so my density is now going to be mass per unit area when we talk about it. But for just a moment, before we really get into that whole density thing, I just want to say, what in the world are we going to do in order to find this? So we're going to need to find an X location, and we are going to need to find a Y location. And so now my center of mass is no longer one-dimensional. It is now a coordinate point, X bar, Y bar. So instead now I'm going to have a system, we still have the system mass. And that is the sum. That is still M equal to the sum, K equal 1 to N of MKs, summing up all the masses. So we're still going to do that. But now we have a moment about the x-axis. And this moment about the x-axis, I'm going to call mx. And I'm looking at the distances the mass is, all right, from the x-axis, and that distance is yk. So the distance that any particular mass, this mass right here, mk, well, this is its distance away from the x-axis, and its desire to rotate about the x-axis is dependent on its distance from the x-axis. Okay, we are out of time, so I will pick up here tomorrow. Now you guys